And we're back. Welcome back, everybody. Shout out, Camille. You're the only one out today, so you should be watching the video.
Hi, Camille.
Camille, the code word is bananas. If you walk in and say, Mr. Laverick, bananas, I will know that you watched the video.
Everybody should know now whether she watched it.
You should have said it at the end.
That's true.
We can do another word.
Yeah, maybe.
No, but that's gonna skip at the end.
No, maybe she doesn't hear.
Okay.
Just give me this part.
You always get the first part. You get to the first part of the note.
To the good stuff.
Yeah.
Get to the good stuff.
You don't like to ramble.
Are you saying I ramble, Popio?
Just a little bit. Oh, yeah.
Okay. So let's just get right to it then. This is section 2.7, derivatives and rates of change. Now, just to review, this is not a ramble. Just to clarify, this is not a ramble. This is a review. We talked about a rate of change, and we went back to the tangent velocity problems, and we said, okay, based on that knowledge, we talked about limits, right? We said, okay, I want the limit to get closer and closer to the slope. And we used that to calculate the slope of a tangent line. We said, I want the slope of a tangent line of x squared to 1, 1. And we found the limit as x approaches a of f of x minus f of a over x minus a. Remember, this is one of our definitions of a derivative, one of our definitions of how we find the slope of a tangent line. We have another one too. And we said, okay, we've got this. Let's plug in x squared. Let's plug in our a value being the x value and see what we get. We got the limit to be 2. And we can use that value of 2, the slope of the tangent line, to create the equation of the tangent line as well. Okay? And then we talked about this definition of a limit. This definition of our derivative, where I can take x and make it go to, make it go to 0. Make the difference. And that's really where we kind of get our term derivative. Derivative is also called a differential. If you get way in advance in mathematics, you'll take a class called differential equations, which is basically you take all the way through calc, and then you take a class called DiffEq, differential equations, which really kind of goes into more about derivatives and how you find derivative equations as well. But we've got these two real definitions of a derivative. We've got the limit as h goes to 0, and then we got the limit as x goes to a, right? And they can be used interchangeably. It just depends on which one it suits you better. Okay. I believe the last one we did was this velocity problem where we said, okay, we got the equation of the distance, right? We got the equation of the displacement, and we said if we find the limit as h goes to 0 of this displacement equation, we get the velocity equation. And that's very interesting, that if we take the derivative of the position, we get velocity. We take derivative of position, we get velocity at any given moment, right? At that moment, at that instantaneous time of time, we looked at time 5, that's instantaneous velocity at time 5. There's no needing to guess about it, right? When we started chapter 2, we said, okay, we think it's going to go to this thing, but we don't really know for sure. We just kind of assume that it's going to reach that thing. Now we can say definitively, yes, using the derivative, we can say that it will be at 49 meters per second at that instantaneous time 5 seconds. And then we said, okay, what's the instantaneous velocity when it hits the ground? Well, after 450 feet, because that's how tall the tower was, it would be at 9.58 seconds, just dividing by the 4.9, square rooting. We say, okay, at 9.58 seconds, at that instantaneous time, the velocity would be 9. Well, there it is, 94 meters per second, right? 94 meters per second. All right. Now, I've been using this term derivative. So let's take a little bit closer look at it. We've seen that the same type of limit arises finding the slope of a tangent line or the velocity of an object, right? We talked about that in 2 different ways. Instantaneous velocity and slope of a tangent line. In fact, limits of the form limit as h goes to 0 of f of a plus h minus f of a over h arise whenever we calculate a rate of change. Rate of change is the same thing as saying derivative. Instantaneous rate of change is the same thing as saying derivative. Okay? It comes up in a wide variety of topics. Anything that you can graph. I was thinking about this yesterday. Anything that you could graph. We've been, looking in terms of the pandemic about like every time the graph rises and falls, every time a peak happens, that it's happened several times since the beginning of this thing. Every time a peak happens, we are very concerned about the rate of change. Well, if we take the data, we can find instantaneous rate of change by finding the derivative, however we create this equation. Maybe it's some sort of regression that we use to find that equation. We can find instantaneous rate of change at any given time period. And that instantaneous rate of change will tell us a lot about what's going on. Like think about in terms of the pandemic, instantaneous rate of change would be instantaneous rate of infection, right? At any given point, we can say, okay, the infection is increasing or the infection is decreasing based on the slope of the tangent line. Think about the slope of the tangent line here. It would be a positive slope, positive slope, positive slope. And then what would happen to the slope right at the peak here? It would go to 0. And then what would happen as I start to decline? The slope would turn into a negative number. So instantaneous rate of change is actually very useful, okay? So if we have this model, we can find when the instantaneous rate of change would turn from a positive to a negative, which means, we're no longer increasing, but now we've hit that peak, now we're decreasing. If we can find a correct equation to model what's going on, okay? That is really finding the derivative. Now, you're going to see this notation here. This f prime of a, that's how we read that. Josie. Yeah, un momento, por favor.
Yeah. Bye tomorrow.
I'm back. Hope you didn't talk about me. It's all recorded. This notation is f prime of a notation. That is how I will note a derivative. Okay? There are plenty of different notations. There's a few different notations to finding a derivative. But this is the most commonly used one. F prime of a. F prime of a. That is saying that is the derivative of that function at a. F prime of a is the derivative of f of x at a. It's the limit as h goes to 0 of f of a plus h minus f of a all over h, which is also equivalent to f of x minus f of a all divided by x minus a as the limit goes to x from a, x to a, as long as the limit exists. And that's kind of a interesting statement right there. We're going to talk about when things are differentiable. That's the correct word to use, differentiable. If the limit does not exist, we would call something not differentiable at that point, okay? That's why we've spent so long on limits, because it ties right in with derivatives. If you cannot find the limit, if you don't know what the limit is, it's not differentiable at that point. If things are discontinuous, it's not differentiable at that point because there's some sort of discontinuity. There's some sort of limit not existing at that point. All right, let's take a look here. Find the derivative of the function f of x is equal to x squared minus 8x plus 9. Now, we have two options. we have two options of finding the limit. We have the a plus h version of the equation, or we have the f of x minus f of a. Let's use the the a plus h. I'm just going to double check, make sure that's the best one to use. Yep.
How do you know which one's the best one to use?
If you start and you're like, oh man, this is going to be a bear to do, that one may not be the best one to use. However, this one is, I mean, it kind of requires a little bit of work here anyway.
Wait, so like, I'm sorry, you lost me a little bit there. Like, how do you pick which one that you're gonna use?
You could use either of them.
Okay, but like, how do you know which one's gonna be easier?
Well, intuition, experience.
Oh, well, I don't have any of those.
Right. So right now you're going to just say, oh, Mr. Robbie's going to hopefully tell me which one is better to use.
Okay.
I will say this, for our purposes here, the one that you're going to use the most is the a plus h one. I would say always start with that one, unless I tell you otherwise.
Okay.
So f prime of a is going to be equivalent to the limit as h goes to 0 of f of a plus h minus f of a all over h. And again, the reason we use that one more often is because it's easier to get the h out of the denominator when it's just a single term down there. It's harder to get an x minus a out of the denominator. All right, so let's evaluate that. Okay, this is the limit as h goes to 0 of f of a plus h. Okay, remember this notation is saying take a plus h and plug it in to the function. All right, so that means it's a plus h squared minus 8 a plus h plus 9. Right? That's f of a plus h. And then minus f of a. I've got to scoot over a little bit. There we go. Minus f of a. Minus this entire thing. A squared minus 8a plus 9. All I did was take a and plug it in for x. This is f of a plus h minus f of a, all divided by h. Now, can I do direct substitution? No. There's an h in the denominator. I cannot do direct substitution. So again, it's down to our fancy algebraic work to try to figure out some way around it. All right, so let's just start reducing. There are things up here that we can reduce. A plus h squared. Okay, that's going to be a squared plus 2ah plus h squared. Remember, I just foiled that. That's just a quick foil. That's a plus h squared. And then we have minus 8a minus 8h. That's just me distributing in the negative 8. And then we have a plus 9. And then I distribute in this negative. Minus a squared plus 8a minus 9. All still over h. Here's where it starts to get fun. Cancel, cancel. Cancel, cancel. Cancel, cancel. Okay. So now we take, let's put the h squared first. I don't know why, it just seems like I should. H squared, and then we'll go plus 2ah minus 8h, all divided by h. Now, what happens with my h's? I could pull one out, but what's going to happen? It's going to cancel one of them out. So yeah, I guess I should show that. Plus 2ah minus 8. Oh, pulled it out and then pulled out. Minus 8 divided by h. Right? So now that's going to cancel. Come on, change colors. And now that leaves me with an h plus 2a minus 8. And that's the limit as h goes to 0 of that thing. Well, now I can directly substitute. What's going to happen with this? That's going to go to 0. And then is it going to touch these two things? No, because I'm not plugging anything in for a. All I'm doing is plugging 0 in for h. So it'd be like 0 plus 2a minus 8. Or in other words, just 2a minus 8. So we can say f prime of a is equal to 2a minus 8. Uh-huh. Oh, cool. So we say that the derivative of that function at a is 2a minus 8. Okay, let's try it again. Now we can do something a little bit more important, because it's good to find the derivative, but you know what's even better? Finding the equation of the tangent line. Finding the equation of the tangent line. Remember that the derivative is really just the slope. Okay, the derivative is really just the slope. The slope at a certain point. At point A. Okay? All right, well, if it's the slope at point A, the derivative is the slope at point A. Oh, yeah, I'm sorry. Where are you going? Oh, study hall. There you go. You're welcome. Thanks for coming in. All right, so again, the derivative at point A is the slope at that value. So if I tell you what point to plug in, maybe point 1, or like x equals 1, or x equals 5, or x equals 10, doesn't matter, you can evaluate what the slope would be. It's f prime of A. So what we can say here is we have this equation where m is f prime of A. Isn't that just point slope form? Y minus y1 is equal to m times x minus x1. And x is a, so we can substitute in y minus f of a, the y value when I plug it in. Like yesterday we were using that 1 comma 1. What y minus f of a is equal to m, our derivative, times x minus a. That is truly going to be our equation of the tangent line. So let's do that. Yes? But we don't want to include h's because we're looking for the equation of the tangent line, which only includes line. So let's now say, okay, the derivative of f prime of a, I see it still back there. F prime of a, I don't know why I'm writing my a's really weird. F prime of a was 2a minus 8. This is still the same equation, okay? Not changing the equation. All I'm doing is saying, okay, let's take it a step further and find the equation of the tangent line. Where? At 3, negative 6. Okay. Well, that means f prime of 3 is 2 times 3 minus 8. Or in other words, 6 minus 8, which is negative 2. So the slope, f prime at 3, is negative 2. The slope of the equation of the tangent line is negative 2. So I can say y minus f of a. You all right?
Just walked in, like,
Saw you.
walked out.
I mean, I had some kids supposed to come in and like finish their test.
Well, he's in that room now, so. Yeah, green hoodie.
Gavin, yeah, he was supposed to come in and finish his test. Okay, I'll get him in a second. Maybe I scared our math scared him off. This is not my class. I don't want to say anything. And then we have x minus 3. So in other words, y plus 6, negative 2, x minus 3. And again, all I did was just take the 3 comma negative 6, plug it in, use the f prime of 3 with my slope. That's where I got the negative 2. Distribute. Oh, look at that. So those 6's will cancel. Y equals negative 2x. Is that really all it comes out to be? Hi, Hunter. Thank you for coming in and not leaving. I had a kid just walk in and leave. You didn't get scared away. You want to go sit in the hallway? Yeah, appreciate it. So my equation is y is equal to negative 2x. Let me double check on that. Seems quite simple, but I guess it's okay. Simple's not bad. Yeah, that's it. So the heavy duty work is finding the slope of the tangent line. Finding the derivative. That's the hard part. Once you get past finding the derivative, you can find the slope of you can find the equation of the tangent line just by plugging in point slope. That's it. Okay. All right. Now let's talk about it in terms of rates of change. Suppose y is a quantity that depends on another quantity x. Thus, y is a function of x. We write y is equal to f of x, right? The difference quotient is really just the slope, right? If we take x to be a difference of x values, and we take y to be a difference of y values, then change in y over change in x, that's just slope, right? So if I find the equation of a tangent line, I am finding the slope. That means for whatever I plug it in at, whatever I'm using to find the slope, whatever I have, and that can include nonlinear equations now. Whatever the difference in the y values are, as it compares to the difference of the x values are, that's really finding the derivative. And finding the derivative is finding the rate of change, the instantaneous rate of change. And that's the important part about how we apply it. It's instantaneous rate of change. It's instantaneous rate of change. That is truly finding the derivative. The instantaneous rate of change is finding, okay, I want the difference in my x values to be negligible. Right? That was our old h, what's now replaced in this equation. Our old h was the difference between x and a, right? The differential on x. Okay, if I want my differential on x to be 0, meaning I want my values to be so close that we call it instantaneous, that's really just finding the limit as I make my x2 my x1. But again, this is really not anything new. This is still just finding the derivative. This is still finding the limit as I make my two x values closer and closer together. And what are we doing there? We're finding the slope as they get closer and closer together, which is the rate of change. Instantaneous rate of change. As my interval on time becomes negligible, my two values come closer and closer together. That tells me that we can assume that that's going to be instantaneous at that point when we do that. Okay. Now, my last couple examples are just application. And I'm not really going to go through the process, the math by it, but I just want to talk about how it relates. Like my first example here. A manufacturer produces bolts of fabric with a fixed width. I can't talk today. Manufacturer produces bolts of fabric with a fixed width. Okay, you guys know what a bolt of fabric is? If you go to Joann's and you see all the fabric on the wall, those are all bolts of fabric. That's what they call those things, bolts. They're wrapped around a piece of cardboard. And I say, okay, they're going to be fixed width. Usually it's a yard, 36 inches. It's going to be a fixed width, so maybe 36 inches. But they're producing bolts of fabric, which means they're unlimited length, right? They can make it whatever length they want, but the width needs to be stuck at 36. That's why, if you look at the wall at Joann's, it's all the same. I don't know why I know so much about Joann's fabric. And then we've got a function of cost. The cost of producing X yards of fabric is C is equal to F of X dollars. Okay, what is the meaning of derivative? That's what I'm really going to look at. I'm not really going to talk about B and C, but I really want to think about what is the meaning of the derivative of the function. What does the derivative of this function actually mean in the context here? Well, remember that derivative is slope, right? The derivative of this thing is slope. Well, slope is change in y over change in x. What is my y value in this case? What is my output of that function? The cost of producing x yards of fabric is C is equal to f of x dollars. So my output is cost. My output is cost. My output is money. Well, then what's my input? Change in fabric. And that's the change in the yards of fabric. Yards of fabric. So what is the derivative truly representing in this case? The derivative is truly representing that at any time when I say, okay, I want to put in 1,000 yards or 50 yards or 500 yards or 5,000 yards, that is the instantaneous change in the amount of money that would cost that different length of fabric would cost. Okay, that is the change, instantaneous change in money, dependent upon the size of the fabric that I'm choosing. Okay, so if I have this equation that's modeling, maybe there's some sort of peak in there where I can optimize my, it's going to cost me so much amount of money to produce this length of fabric. Maybe there's a peak in there where if I start making more of that, then it's going to go down because maybe I've got too much supply and not enough demand. Or maybe I'm not making enough to meet that supply and demand. And maybe I'm cresting to a certain point where supply and demand match. And I'm optimizing my length. That's truly finding the derivative. What is the exact value where I can find the change in price dependent upon my change in fabric? If I change my fabric, what's going to optimize my best price? Okay, so that's what that means in terms of that one. Let's take a look at another one. This is a different function. D of t is our national debt. The table in the margin gives the approximate values of this function by providing the end of year estimates in billions of dollars, 1985 to 2010. Interpreted estimate, the derivative. What is the derivative of this function? If you're looking at the interpretation of the derivative, you need to find basically the slope, because that is the derivative. You're back. He's back. Is this the guy that walked in and walked out?
Yeah.
There you go. Just trying to see the hallway there. Again, so if we want to interpret the derivative, we're going to find the change in slope. We're going to find the change in y as it pertains to the change in x. So what's my y value here? What's the y value in the table? Providing end of year estimates in billions of dollars. That's our debt. That's the national debt. Change in debt divided by change in x. Well, what's time? Oh, what's x?
It's time.
Change in time. Okay? So, okay, change in debt divided by change in time. So what is the derivative truly representing? The derivative is truly representing the instantaneous change in debt at any particular time. The instantaneous change in debt at any particular time. And you have to talk about it in terms of change in debt. It's not the instantaneous debt at any time. No, that's just the value of the function. If I talk about the value of the derivative, you're talking about the rate of change of that thing. The rate of change of debt at any given time. Instantaneous rate of change. So I could say, okay, if I had this function, what was the rate of change of debt at, 2001, or December of 2001, and I could find that instantaneous rate of change of debt. That's how fast it's moving up or it's moving down, right? If this slope comes out positive, then my derivative is positive. That means the slope is positive. That means it's going up. If my derivative comes out negative, that means the debt is moving downward. Okay? Same thing if I was talking about that whole bolts of fabric thing. If the derivative came out positive, then my cost is going, my profit is still going up. If that comes out negative, then my profits are on a decline. Okay, we're going to talk at great length about when the derivative comes out positive or negative and what are the implications on that function. Okay. All right, so that's it for the notes for derivatives and rates of change. I will stop talking now. I'll stop rambling, as Popio called it.